Hello viewers, welcome to Physics with Sanmitra. I am Sanmitra Bhomik, and in this lecture series we are learning about special theory of relativity, a very introductory discussion on this topic. And let us learn about Lorentz transformation. We have learned about Galilean transformation where we find the position, that is where we relate one inertial frame with respect to another. Now in that case we had taken an approximation that this velocity v, that is less than c, that means we did not consider the effect of velocity v. Now in this case, if the velocity of v and c are comparable, like say if velocity v is 0.1 times is greater than equal to 0.1 times of c, then we cannot apply the Galilean transformation directly. There what is happening is that this time, what we took that time as absolute value while deriving Galilean transformation, if you remember, we took t dash is equal to t, because in classical physics we take time as absolute quantity, but in case of relativistic physics that is not true, and we'll see that later. However, I am not deriving the Lorentz transformation since this is a very introductory discussion on STR. I am just stating them. I will teach you how to apply them, but I am not deriving them. So this is my frame 1. I am assuming this to be x, y, z, and this is my frame 2. I am assuming it to be x dash, y dash, z dash. So this is this frame 2, and this is my frame 1. This is f1, this is f2. F2 is moving with respect to f1 with the speed v, and let's say v is comparable to c. That means it is not very less. Let's see here what is happening. Now we can write the Lorentz transformation. Lorentz transformation, TRN, Lorentz transformation. I'm writing in short. X dash, that is the new frame that I can write. X minus Vt divided by root over of 1 minus v squared by c square. Let me write one thing here. Let me take an approximation here, or a notation. X minus Vt divided by root over of 1 minus v squared by c squared, where gamma is equal to 1 by root over of 1 minus v squared by c squared. We will be using gamma a lot. Y dash is equal to y, z dash is equal to z, t is equal to, now time t dash, time we had taken as constant, I mean absolute, that is same, but here it is not true. See, speed of light will be constant. I am telling you again, the speed of light will be constant for any frame. So to adjust that, the length and the time will be changing. So time is not absolute. That is what we learned in the classical physics, but here time will not be absolute. This time will be t minus vx by c square divided by 1 minus v squared by c square. I have not derived it, but you can check the derivation in any book if you want to. Now let me show you what is inverse transform. Inverse transform, that means we related the transformation, inverse transformation. We related f2 with f1. Now we relate f1 with f2. That is x with x dash. X will be x plus vt divided by gamma into gamma, or I am writing the full only, minus v squared by c squared. Y dash, y will be equal to this x dash. Y will be y dash. Z will be z dash, and t will be t dash plus vx by c squared root over of 1 minus v squared by c squared. Just what we are doing, we are replacing v by minus v. That's it. We are replacing v by minus v. So this is my transform. This is how we are transforming, and why we are doing this inverse transform. Actually why we are doing this. This is my frame f1. This is my frame f2. This f2 is moving with a speed v with f1. So I can assume that if I assume f2 be at rest, then relative velocity I can assume that f1 is moving with a speed velocity of minus v with respect to f2. That is why we are just replacing b by minus v. So that's all for this video, and if you like our content, then please subscribe to our channel and click on the bell icon.